In this video, we will continue with the beam design calculator program. At this point, we have determined what the z of x required is. So now you would go to the website and figure out what size member you would need, or the lightest member that would have a z of x greater than this. So now that we have the member chosen, we can figure out some of the properties and dimensions of it. So I'm going to want to know the z of x. I'm going to want to know the thickness of the web, the height of the web, the d, the depth, as well as the inertia in the x direction. So let's continue with the formatting. So I'm going to maybe center all these. I'm going to want to add borders, not the thick ones, those thinner borders. And then I'll probably want to add a thicker border around everything, and then maybe make this thicker. Oh, that's not what I wanted. I wanted the borders. And all of these are going to be yellow because those are all user inputted. And then it's good to keep the dimensions shown. Inches cubed, this would be in inches, inches, and then inches to the fourth. Okay? Now we are ready to check for shear. So with shear, I'm going to merge this and call this shear. When we're doing shear, we are looking at the shear applied, and we're comparing it to the shear strength. And then we're going to see if it's good or bad. So yay or nay. Okay, let's center these. So the shear applied is going to be the maximum shear right here multiplied by the factor of safety, which is 1.5. So I'm going to say that this cell is equal to max shear multiplied by 1.5. Again, if you want the logic, you can say if C11 equals quotation, quotation, comma, quotation, quotation, comma, C11 times 1.5. The shear strength was that equation. Let me see if I can quickly find it. The 0.6, yeah, right here. 0.6 FW times FY times A of W. So that's going to be, right here, is equal to 0.6 multiplied by KSI right here, multiplied by the area of the web, which is this cell times this cell. And I made a mistake. This is supposed to be in inches, not inches cubed. I think it auto-filled it before. Okay. So let's center it. And now, let's put in some values here just to keep it happy. I'm just totally making up numbers right now. Excuse me. So now, we can see that the shear strength is greater than the shear applied. Of course, I made up those numbers, but you can then give yourself a little check. If this cell right here is greater than or equal to this cell, then we're happy. We're going to say, yay. If it's not, then boo. Yay. But what if I made this really, really, really tiny? Boo. So just showing you how logic can help you along the way. Didn't want to merge it. I wanted some borders. I don't want the really thick borders. I want that one for all of them. And then I like to go back and add, keep hitting that, the thicker outside borders for all of it. Okay, so now these two cells are also going to be that, was it that one or maybe it was this one? That one looks better. This cell, I like to make it green because I feel like that's like a good answer cell. And then this cell right here is going to be green because that's like a final check. Now we're ready for deflection. So let's copy this down just to get the formatting. Delete everything here because it's not going to be the same by any means. And we're going to say deflection. And we're going to say allowed and then actual. And then we'll do yay or nay again. Maybe we should say true or false. Be a little more professional, right? True or false. Or you can say good or bad. It doesn't really matter. So when we do deflection, you might remember we actually have to do it twice. So I'm going to copy that down. And we're going to have to do it for dead load plus live load, and then again for just live load. Okay, I'm okay with the thick borders for all at that time. If you want, you can always add like another little one to the left. Makes it look a little bit nicer. Okay. The allowable deflection is going to be L over 240 for dead and live, and then L over 360 for just the live load. And remember, that must be in inches. So I'm going to say that the allowable is equal to the beam length multiplied by 12 divided by 240. And the second one is equal to the beam length multiplied by 12 divided by 360. So these are the allowable deflections for both scenarios. Now we got to figure out the actual deflection. The actual deflection is given by the formula. Let's go back to the finished product just to see this chart again. PL cubed over 48 EI. PL cubed over 48 EI. All right. So it's a little bit hard to type it in. Let's see if we can get it in the first try. Equals P. And this is dead and live, so I'm going to say this P. Got to multiply it by 1,000 because I want it in pounds. P times L, which is this one, times 12 because I want it in inches, raised to the third power, PL cubed divided by, make sure you have parentheses, 48 multiplied by E multiplied by I. I guess that's everything. Why is there an error? What did I do wrong? I don't know why that was the difference, but okay, we got it to work. Of course, I made up these numbers over here, but you can kind of self-check. If you have 0.00001, you're off. If you have 1,000, then you're off. It should be somewhat in the ballpark. So that was the first one, and I'm gonna copy the same thing. I'm not gonna drag it down because that'll add everything by one. I'm just gonna copy everything. And for this one, the only thing different is really that this is just the live. So instead of C6, I'm gonna make it C5. And that's it. So then over here, I'm gonna see the logic test. If allowed is greater than or equal to actual, comma, actually I think I'm going to do good or bad. So I'm going to make this good and bad. And then same with this. I'm going to copy that logic down because, okay. Now we're pretty much done. The last thing that I like to do is if this does not work for deflection, we might want to know what inertia is required. So if the actual deflection came back as too much deflection, we need to choose a new member with a larger inertia value. Let's go back to the PowerPoint to see what we do. We did that example where we checked the deflection and we found that the deflection did not work. So what do you do when it doesn't work? You cry and then you choose a new member. So I'm going to take the actual deflection, divide it by the allowable deflection, which will give me a value greater than 1, and then multiply it by the original I to give me a new I that is required. And that'll be the I that I choose a new member based on. So let's just do a new thing, and we'll call this, I hope I have enough time, if deflection, I think I spelled deflection, fails. And I'm going to say that this is going to be, actually let's do it over here. If fails, I'm going to say that this is going to be actual divided by allowed multiplied by the original I. I'm going to delete that. I have a better idea. That's what happens when you do these live. You don't get to have everything in front of you all at once. So we're going to call this required I. And I'm going to now know exactly what inertia is needed. And we're going to copy the logic down, but we're going to have to change this because it's now over here. I'm going to make it M9. Right, so then it's going to be the actual divided by allowed multiplied by the I. So I'm going to hit unmerge and then merge again. And then these I'm going to give, just to keep it nice and pretty. I like pretty charts. Okay, so then the required I, if it failed, would be the maximum of these two. You can even make another one that's like, hey, equals the max of these two cells would be the required I. So then I can call this, see how I'm changing as I go. This is kind of how the programs are going to be. You maximize as you go. Over here is really the required I of X. And this cell right here is the one that you would be using. So I'll make that green. And then these are intermediary. And yeah, now we would have that. Okay. Think that's it. I think we're gonna stop here, and then in the next one we will go through an example problem.